Today our topic is analytic function. Let a D to C be a complex function where D subset of C and Z0 be a point of D. Then it is said to be analytic at Z0 if f is differentiable in some neighborhood of Z0. That is, if there exists a neighborhood of Z0 where f is differentiable at each point in this neighborhood, then f is said to be analytic at Z0. Clearly, if f is analytic at Z0, then f is differentiable at Z0. That is, analyticity implies differentiability at a point. Now, f is said to be analytic on D if f is analytic at each point of D. Now, we give an example to show that analyticity and differentiability are not equivalent conditions. That is, we give an example of a function which is differentiable at a point but not analytic at that point. Let us consider a complex function fz equal to x square plus I square. The real part of the function u is equal to x square and imaginary part v is equal to y square. Now ux equal to 2x, uy equal to 0, partial derivative, and partial derivative of v with respect to x equal to 0, vy equal to 2y. Now, by sufficient condition of differentiability, if uv satisfies here equation and partial derivatives of uv with respect to x and y are continuous at a point, then f is differentiable at that point. Now, here uv satisfies here equation when ux equal to vy and uy equal to minus vx. That is 2x equal to 2y implies x equal to y. So, the point on this line y equal to x, f is differentiable. That is, f is differentiable at each point on this line y equal to x. But f is not analytic at any point on this line. As if we take any point from this line and take any neighborhood of that point, then there exists infinite number of points outside this line. At this point, f is not differentiable. So, f cannot be analytic at this point. Here, f is nowhere analytic and differentiable at each point on this line. We now define domain. A domain is a non-empty, open and connected sets. D is called a domain if it is non-empty, open as well as connected. If D is a domain, then the converse is also true. That is, if f is differentiable at each point on this domain, then f is analytic on D. We now give three important consequence, that is result of analytic function. Suppose f from D to C be an analytic function where D is a domain, and if real part of fz is equal to constant, then f is a constant function. If f equal to u plus iv, then by given condition u is constant. So ux equal to 0, uy equal to 0. Since f is analytic on D, that is f is differentiable at each point on D, so uv satisfies Cauchy-Riemann equation. So ux equal to vy and uy equal to minus vx for all xy belongs to D. Since ux equal to uy equal to 0, so vx equal to 0, vy equal to 0 for all xy belongs to D. Since D is connected, vx equal to 0 implies v is free from x. Similarly, vy equal to 0 implies v is free from y. That is, v is a constant. Given u is constant and we get v is constant, so f equal to u plus iv is a constant function. Now, we prove that if f is analytic on D where D is domain, and if dash z equal to 0 for all z belongs to D, then f is a constant function. F is a constant function. We know if f equal to u plus iv, then f dash z equal to ux plus ivx at xy, where z equal to x plus iy for all z belongs to D. Since f dash z equal to 0, so ux equal to 0 as well as vx equal to 0 for all xy belongs to D. Since f is analytic on D, so uv satisfies CR equation at each point on D. So ux equal to vy and uy equal to minus vx for all xy belongs to D. So uy equal to 0 and vy equal to 0 for all xy belongs to D. Since the domain is connected, ux equal to 0 and uy equal to 0 implies u is free from x as well as y. That is, u is constant. Similarly, v is constant on D. Since both u and v are constant, so u plus iv, that is f, is constant on D. Now we prove another result where f is an analytic function on D and mod of fz is equal to constant on D. Then fz is constant on D. Suppose f equal to u plus iv and mod of fz is equal to k, where k is a constant. This implies u square plus v square is equal to k square for all xy belongs to D. Now we consider two cases. In first case, suppose k equal to 0. since both u and v are real valued function, so u square plus v square equal to 0 implies both u equal to 0 and v equal to 0 for all x y belongs to D. Since both u and v equal to 0, so if z equal to 0 for all z belongs to D. That is if each constant. Case 2, suppose k not equal to 0. Here u square plus v square equal to k square for all x y belongs to D. Now differentiating partially with respect to x, we get 2u ux plus 2vvx is equal to 0. That implies ux plus vvx equal to 0. Again, differentiating partially with respect to y, we get uuy plus vvy is equal to 0. Since f is analytic on D, that is f is differentiable at each point on D, so uv satisfies shear equations on D, that is ux equal to vy and uy equal to minus vx for all x y belongs to D. So from this relation, if we put minus uy in place of vx, we get ux minus v uy equal to 0, and if we replace vy by ux, then we get vux equal to 0. Now multiplying this first equation by u and second equation by v and adding we get, that is we want to eliminate uy from this equation. We get u square plus v square into ux is equal to 0. U square plus v square equal to k square. Since k not equal to 0 in this case, we get ux equal to 0 for all xy belongs to D. And if we put ux equal to 0 in this equation, we get if we put in this equation, we get vvx equal to 0 for all xy belongs to D. So this implies either v equal to 0 or vx equal to 0. If v equal to 0, then vx is also 0 because partial derivative of 0 function is also 0. So from this equation we get vx equal to 0 for all xy belongs to D. So ux equal to 0, vx equal to 0 for all xy belongs to D, and if we satisfies shear equation, so from this equation we get ux equal to 0, uy equal to 0, vx equal to 0, vy equal to 0 for all xy belongs to D. That means in each connected set, both u and v are constant function, and this implies fz is a constant function. Now we define harmonic function. A real valued function of two variables x, y. A function phi of real valued function phi of two variables x, y is called harmonic function if second order partial derivative of phi, all the second order partial derivative of phi are continuous and phi satisfies Laplace equation, that is phi xx plus phi yy equal to 0. Then phi is called harmonic function. Harmonic function. we now show that if f is analytic on D, then both real part and imaginary part, that is u and v, are harmonic functions. To prove this result, we now use an important result. What is the result? If D is a domain and f from D to C, f is a complex function, if f is analytic on D, then all the derivative function of f exist and analytic on D. That is, if D is a domain and f is an analytic function on D, then all the derivative function of f exist and they are also analytic on D. This is an important and powerful result of analytic function. And using this result, we now prove that if f is analytic on D, then both the functions, that is both the part, real part as well as imaginary part, u and v, are harmonic function on D. Here f is analytic function on D, where f is equal to u plus iv. Since f is analytic function on D, that is, if we differentiable at each point of D, show the real part u and imaginary part v satisfy Cauchy-Riemann equation, that is ux equal to vy and uy equal to minus vx for all xy belongs to D. Also, since derivative of f is also exist and analytic on D, so uxx, uxy and uyy exist and continuous on D. Similarly, the second order partial derivative of v exists and continuous on D. Now, differentiating partially with respect to x, we get from this equation we get uxx equal to vxy, and differentiating partially with respect to y, we get uyy equal to minus vyx. Since the second order partial derivative of v exists and continuous, so vxy equal to vyx. So from this we get uxx plus uyy equal to 0 for all xy belongs to D. That is, u satisfies Laplace equation. Since the second order partial derivative of u exists and continuous on D and it satisfies Laplace equation, so u is a harmonic function on D. Similarly, if we take derivative, partial derivative with respect to y, of this equation we get vyy is equal to uyx, and differentiating partial with respect to x, from this equation we get vxx is equal to minus uxy, and from these two equations we get vxx plus vyy equal to 0. Since uxy equal to uyx, so both u and v are harmonic functions. If u and v are harmonic function and uv satisfies Cauchy-Riemann equation, then v is called conjugate harmonic function of u. That is, two functions. A function v is said to be a conjugate harmonic function of u. If both u and v are harmonic function and uv satisfies Cauchy-Riemann equation, that is ux equal to vy and uy equal to minus vx, then v is called conjugate harmonic function of u. We now give an example. টু মেথড মানে আমাদের আমরা একটা মেথড এখানে বলবো যেখানে ইউ ফাংশনটা দেওয়া থাকলে আমরা ভি ফাংশনটা বার করতে পারবো সেখান থেকে আমরা এফ দ্যাট ইজ ইউ প্লাস আইভি বার করতে পারবো যেটা হচ্ছে অ্যানালিটিক that is given a function u we now find a function v such that u plus iv is analytic function. Suppose u is equal to e to the power x cos y for all xy belongs to R2 for all xy. Our target is to find a function v such that f equal to u plus iv is analytic on C. First, we show that u is a harmonic function. If u is not a harmonic function, then we cannot get any analytic function f such whose real part is u. There ux is equal to e to the power x cos y and uxx equal to e to the power x cos y. Uy equal to minus e to the power x sin y. Uyy equal to minus e to the power x cos y. So uxx plus uyy equal to 0. That is u is a harmonic function. If f equal to u plus iv is analytic, then u will satisfy Cauchy-Riemann equation. So ux equal to vy and uy equal to minus vx. From this equation we get vy is equal to ux, that is e to the power x cos y. Now integrating with respect to y, we get v is equal to e to the power x cos y dy. y সাথে যেহেতু ইন্টিগ্রেশন করছি আমাদের যেটা ইন্টিগ্রেটিং কনস্ট্যান্ট একটা ফাংশন অফ x আসবে, সাপোজ দিস ইজ ইকুয়াল টু phi x which is an integrating constant. The e to the power x sin y plus phi x. Now differentiating partially with respect to x, we get vx over e to the power x sin y plus phi dash x. Now vx equal to minus uy, that is uy equal to it minus e to the power x sin y, so this is equal to e to the power x sin y. So we get e to the power x sin y equal to e to the power x sin y plus phi dash x. So this implies phi dash x is equal to 0. This implies phi equal to constant. Phi is a constant function. Since this is a function of x only and phi dash x equal to 0, this implies phi is constant function. So v is equal to e to the power x sin y plus c. So we have given u is given, we find v. So corresponding complex function f সমান u plus iv is analytic. এখানে আমাদের যেটা হচ্ছে আমাদের কোনো হারমোনিক ফাংশন দেওয়া থাকবে তার করেসপন্ডিং আরেকটা আমরা ফাংশন বার করতে পারবো v such that u plus iv হচ্ছে analytic.